Hello students, welcome to EPG Pathshala. I am Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, and today we are going to discuss about the module Quantum Hall Effect from the paper Solid State Physics. After studying this module, you will be able to understand first the classical Hall effect, learn about origin of Landau levels in two-dimensional electrons in magnetic fields, learn about how the energy levels in two-dimensional electronic systems are quantized, learn how to estimate the degeneracy, also learn the origin of plateaus in the plot of Hall voltage versus magnetic field. The quantum Hall effect is one of the most striking and surprising developments to occur in physics in the last 20 years. The integer quantum Hall effect manifests itself as a series of plateaus in Hall resistance RH of materials containing two-dimensional, that is 2D electron systems. This two-dimensional actually means 3 dimension but is very thin, of the order of around 100 angstrom. The most common example of such a system is the MOSFET and semiconductor heterojunction. The important thing is that the electrons can move freely in a 2D plane but not in a perpendicular direction. There are two fundamental ingredients for the understanding of the Hall effect. First is the Landau quantization of states induced by the magnetic field in the 2D electron motion, and second is localization. Now if we plot a graph between B, the magnetic field, and RH, the Hall volt resistance, it should come out to be a straight line, which is classically. But if we have a very thin conductor and at very low temperatures, at around temperature of 50 millikelvin, it exhibits a series of plateaus. So students, as you can see from this schematic figure, that this Hall effect actually, there are 4 different types. The one that you already know of is the classical one, and then on the left hand side, as you can see, which is called as the integer quantum Hall effect, and on the right hand side it is a fractional quantum Hall effect. Recent version is the spin quantum Hall effect. So let us now start discussing, starting from the classical Hall effect, which you already know of. So this was an experiment which was conducted in 1879 and goes after the name of the scientist who performed this experiment, and the schematic figure is actually shown here on the left hand side. And as you can see from here, the directions of the magnetic field, the force acting on the electron because of the magnetic field, and the direction of the velocity is shown also. Now of course, without going into the much detail which you probably might have studied already, the value of sigma is given here on the right hand side, as you can see from here. And what does it indicate? That it's given in the matrix form. As you can see from here, that in the matrix you have the diagonal element sigma xx and sigma yy, and the off diagonal elements is sigma xy and minus sigma yx. So this WB basically is the frequency, which is the product of E into B divided by m star, where m star is the electron mass, and the sigma at B equal to 0 is E square and tau divided by m star. So this is basically the expression that you get from the classical Hall effect. Now the resistivity, which is basically sigma inverse, is something which shown in the previous slide. You just invert this matrix, and as you can see from here, that this rho xx and rho xy is defined like this, the values, and also a plot is shown here. So this rho xx, now as you can see, plotting as a function of B, it remains constant, and this is also visible from the expression for rho xx. that it's a straight line, no dependence on the magnetic field. While on the other hand, rho xy is directly proportional to B and increases linearly as B is increasing. So this is the typical results that one already learns from the classical Hall effect. So this sort of trying to understand the classical Hall effect is important, because when you want to go into the quantum Hall regime, this is something which comes in as a comparison. The resistivity formula is again written here just to make you understand. What happens when you have this WB into tau very high. That is, either you have very high magnetic field, because WB depends upon the magnetic field, which is, let's say, make it large as more than 2 Tesla, and other hand you have a low temperature less than 4K and a two-dimensional electron gas that you can have. In such a situations, this graph of Hall voltage versus the magnetic field, it gives some very surprising results. So this first surprising result was observed in 1980, and the graph that you see here is the first experimental observation of the quantum Hall effect. Now in this plot, show the two curves. One is rho xx and the other is rho xy. So as you can see from here, that the rho xx plot shows some peaks at some very specific values, and the plot of rho xy, the curve of rho xy, shows also some interesting results, that you have a linear increase, but in between you have these plateaus, right, where the Hall, when you change the magnetic field, nothing happens with the plot. It's a constant straight. So what does this indicate? This is a very important point. And also you will observe that the peaks in rho xx happens more or less at that particular point where the plateau ends and it again starts to rise. Just carefully notice this, and you will really appreciate how the two plots are varying with the magnetic field. So in the context of this particular graph that we have observed, so we will discuss something about these two-dimensional electrons in a magnetic field and the origin of Landau energy levels. The physics is very much different as compared to a three-dimensional case. Okay, so let the electrons be confined to the xy plane and the magnetic field be parallel to the z-axis. Understand the situation? The Hamiltonian for such a system is given by the following expression. Now, as you can see from here, the A here is the vector potential associated with the magnetic field, that is B, which is the magnetic field, is equal to del cross A. So in the Hamiltonian, as you will see, that you have only the x and y component of the vector potential and also that of the momentum. So what exactly does this mean? So this means that you have a two-dimensional gas of electrons, that is, you have a confinement of the electrons only in the z direction. It is not able to move in the z direction, but it is free to move in the xy plane. So that is why we call it the two-dimensional electrons. And the magnetic field, of course, is applied parallel to the z direction. Under a suitable gauge, we are free to choose A, under which B remains unchanged. This is also a very important implication. Now, continuing with the origin of the Landau levels, let us suppose that we choose the vector potential A is equal to minus YBI. So, of course, A is found out from an expression which we had given in the previous slide, that is B is equal to del cross A. So that is how we find out. So we choose A like this. So the Hamiltonian reduces to this expression. Now since the coordinate x does not appear in H, and since we know the commutators of y px and py and px is equal to 0, it follows that h with px is equal to 0. This means that px is a good quantum number and may be regarded as a constant parameter. We define k equal to px divided by h. The eigenfunctions of the problem must now simultaneously satisfy the following two equations. Okay, so these two equations, that px into xi is equal to h cross k xi and h xi is equal to e xi. So the second equation is very familiar to you. It's just basically nothing but the Schrödinger equation. So now, continuing with the origin of Landau energy levels, since the operator px is given by minus iota h cross partial derivative with respect to x, the first equation yields the desired result. That is, the wave function is equal to a product of a plane wave e raised to power ikx into the phi, which is a function of y. The quantum Hall effect has analogy to the one-dimensional simple harmonic oscillator. We can see that the Schrödinger equation reduces to the one-dimensional problem. Now, the Schrödinger equation that we had seen is given like this: h xi is equal to the following expression. So one has to simplify this a bit, little bit of manipulation is required, and finally we will get this expression in the final one, that h xi is equal to e raised to power iota kx brackets m omega c square by 2 into y minus y naught whole square plus py square by 2m brackets close multiplied by phi as a function of y, where this omega is eb by mc and y naught is equal to h cross kc divided by eb, where omega c is known as the cyclotron frequency. The right side must equal E xi is equal to E into e raised to power iota kx phi y. Thus the differential equation is obtained after replacing py by minus iota h cross partial derivative with respect to y. So this is the expression that we finally obtain for this gas of two-dimensional electrons in a magnetic field, and this is basically the Schrödinger equation, right? Now what we have to do is that now we have to begin by recalling that the ordinary one-dimensional Schrödinger equation for a simple harmonic oscillator with frequency omega is written like this. Okay, here as you can see that you have z instead of y minus y naught. So where the z is a dummy coordinate, our problem looks very similar except we have a term y minus y naught whole square instead of just y square. But this simply means that the center of the oscillations is at y equal to y naught rather than at y equal to 0. As we can see by making the change of the variables z equal to y minus y naught. For any given y naught, that is for every k, our problem is exactly like the corresponding 1D simple harmonic oscillator. Most important, the energy levels for the two problems must be the same. From our knowledge of simple harmonic oscillators, it should be no surprise that the expression for En is equal to n plus half h cross omega c, where n is equal to 0, 1 and so on. These are integers. So this is basically what? These energy levels which you see here is the harmonic oscillator levels. This is a remarkable result actually. The allowed energy levels for a free two-dimensional electron moving in a magnetic field are identical to a fictitious 1D simple harmonic oscillator. Note these levels are discrete. With the magnetic field, the electron's energy is a continuous variable. Note also that the energy levels do not depend on the value of y naught or therefore k. The momentum k in the x direction creates no kinetic energy. Each value of n can have apparently any value of k, and thus the energy levels are highly degenerate. Thus the magnetic field has induced a great condensation of the continuous energy spectrum of a free particle in two dimension into a discrete set of highly degenerate levels. These levels are known as the Landau levels, are equally spaced by the cyclotron energy h cross omega c, which is itself proportional to the magnetic field strength. The gaps between the levels are void of electronic states. For 3D electrons, no such gap occurs. So now, after finally showing that the two-dimensional electron gas in one specific direction, the energies are quantized, next we go ahead and try to see and estimate the degeneracy. So we have Y naught is equal to h cross kc divided by Eb. Now, along the x-axis, the electron behaves like a particle in a box, and its k values are given by k equal to 2 pi n divided by Lx, with n equal to 0, 1, 2 and so on. And here remember, this Lx that you see is basically the dimension along the x direction. So substituting the value of k into the expression for Y naught, we get Y naught is equal to h cross 2 pi nc divided by Lx Eb. Now let Y naught max be the maximum value Y naught can take, and correspondingly capital N is the maximum value of n. So putting in these substitutions into the expression for Y naught, we get the expression for Y naught max, which is equal to h cross 2 pi capital N into c divided by Lx Eb. N is the number of states available in each Landau level, but the maximum value of Y naught is Ly, that is the physical dimensions of the sample, so that the electron stays within the sample. So Lx into Ly is equal to h cross 2 pi nc divided by Eb, and capital N divided by Lx Ly is equal to Eb divided by h cross 2 pi c, which is equal to Eb by hc. But N divided by Lx Ly is the number of states per unit area in a Landau level. So let us call that N naught is equal to the degeneracy per unit area. So N naught is equal to Eb divided by hc, which is equal to B divided by phi naught, where phi naught is given by h into c divided by E. If exactly j Landau levels are completely filled, the total number of electrons per unit area should be j multiplied by degeneracy per unit area. Okay, so ns is equal to f into E into B divided by h cross, where f is, these are the integers 1, 2, 3 and so on, and the Hall resistance is now RH, which is given by B divided by ns, which is equal to BHC divided by FEB E into C. So finally we get an expression H divided by FE square. So F is are the integers as shown here 1, 2, 3 and so on. Also shown in this slide is a figure on the right hand side. This is the density of states for a 2D electron gas in a magnetic field. So as you can see from here, that for an ideal two-dimensional electron gas, these are delta functions at exactly at these points, that h cross omega c by 2, 3 times h cross omega c by 2 and so on. But because of collisions and impurities, there's a slight broadening. So also shown is a broadening here. So the case of ideal and also with broadening, this is shown here. Now students, also remember, impurities play a particularly important role in the ordinary electrical resistance of metals and semiconductors. Much of the energy dissipation that characterizes resistance occurs when the electrons are scattered by collisions with impurity atoms or defects in the crystal lattice. Paradoxically, the presence of impurities is what leads to the disappearance of the electrical resistance and the plateaus in the Hall resistance that constitutes the quantized Hall effect. In the presence of impurities, the many independent quantum states that make up a given Landau level are no longer precisely equal in energy. The single energy level that makes up a given Landau level in a pure crystal is thus spread out in the presence of impurities into a band made up of many distinct energy levels. The various quantum states in each energy band can be divided into three general classes. The states near the bottom of each band, those of the lowest energies, are each localized in small regions of sample. 2. Near the top of each band are the high energy localized states, perhaps in the region around the impurity atoms that have acquired electrons and have excess of negative charge. 3. Near the center of each band are the extended states, which are spread out over a large region of space. 4. The localized and extended states are distinct because the electrons in the localized states cannot move very far and cannot carry current. The energy of the highest field electron is known as the Fermi energy. In each region of space, the states with energies below the local Fermi level are occupied and above it are empty, which is something which you already know, students, even from the three-dimensional solid state physics you have learned. Suppose a current is flowing along a sample in a perpendicular magnetic field and the Fermi level of the sample's electron is in the subband of localized states near the top of some Landau band. In this case, all the extended states and the low energy localized states of the Landau band will be completely filled, and some of the high energy localized states will be occupied as well. Now suppose that the strength of the magnetic field is gradually increased and that at the same time the current is continuously adjusted in such a way that the Hall voltage between the sample's two edges remains constant. This figure also on the left hand side is showing something which I have just said here. As you can see in that here you have the Landau level and then you have all these energy levels corresponding to that Landau level, and you will see here that this Fermi energy is situated somewhere around the top and below it are all occupied, that is the dark band which you see are basically the occupied ones. And this again in the extreme right you see those energy levels when the magnetic field is actually increased. So as you can see from here that once you increase the magnetic field, this Fermi level actually goes down, visible from the second figure. Now many of the newly available states will be below the local Fermi level, and so electrons from higher energy occupied states will drop down to fill them. These electrons will in general come from the high energy localized states that are near the Fermi level. As these states are vacant, the Fermi level, the energy of the highest occupied level, descends to the lower position within the Landau band. As long as the Fermi level remains in the subband of the high energy localized states, all the extended states within the Landau band remains fully occupied. Because the number of independent quantum states with per energy unit area is directly proportional to the applied magnetic field, and as the magnetic field increases, the number of independent quantum states in each Landau level increases proportionately. Since the Hall voltage is being held constant, the fact that the current does not change as the magnetic field is varied implies that the Hall resistance also remains constant. Whenever the Fermi levels is in the subband of localized states, then the Hall resistance remains the same even when the magnetic field is varied. This is the plateau in Hall resistance that is characteristics of the quantized Hall effect. Eventually, as the strength of the magnetic field is increased, the supply of electrons in the high energy localized states will be exhausted and the Fermi level must drop into the sub-band of extended states. As the Fermi level descends through the sub-band of extended states, some of them are vacated. Because the current carrying sub-band is then only partially occupied, the amount of the current flowing decreases and the Hall resistance therefore increases. The Hall resistance continues to increase when the magnetic field is increased, as long as the Fermi level remains in the sub-band of extended states. If the magnetic field is increased further, eventually the extended states within the Landau band will all be emptied and the Fermi level will once again enter a sub-band of localized states. The low energy localized states at the bottom of the Landau level. If there is at least one full Landau band below the Fermi level, the extended states in that band will be able to carry a current and the quantized Hall effect will once more be observed. Because the extended states of one Landau band have been completely empty, however, the number of subbands of occupied states has been reduced by 1. So, this figure here shown in this slide actually nicely demonstrates what I have just said. As you can see that energy is plotted as a function of density of states. Now, on the extreme left you have the case when you B is equal to 0, and up till the Fermi level you see that everything is filled, this occupied by the electrons. Now, in the presence of the magnetic field, the next on the right hand side you see two plots. So, in the middle you have a certain value of the magnetic field, and as you can see from here that there are two energy levels, broadened energy levels below the Fermi level and one above. So, the one which are two which are below, they are shown by dark shading, which is basically indicating they are occupied by the electrons, and the spacing is h cross omega b. And on the beyond the Fermi level above, you have vacancies. These energy levels are not shown shaded. Now, as you increase the magnetic field, the extreme right curve shows that one energy level which is still below the complete energy level is completely filled, and just at that particular point, this Fermi level, you see half of the energy levels lies below, half of the energy level lies above. So, the half which is lying below is completely filled and one that is lying above is completely empty. So, you see that how the magnetic field is changing and how these bands, they keep on, the level of these bands keep on changing, right? And then alternately, what is happening is that you have complete filling, no filling, partial filling, and this keeps on changing like this. So, students, let us summarize what we have learned in this module. So, we have learned about the classical Hall effect. We have learned about the origin of the Landau levels in 2D electrons in the magnetic field. We have learned about how the energy levels in 2D electron systems are quantized. We have also learned how to estimate the degeneracy. And finally, we have also learned the origin of plateaus in the plot of Hall voltage versus the magnetic field. Thank you.